for giving me this opportunity to talk about my work. So I'll be, as he said, I'll be talking about constraining, how we constrain spectral densities in thermal field theories, conformal thermal field theories, and this is based on these two sets of works. And so I'll motivate my problem in in a different manner, as in I'll talk about some the parameters of 3-point function for zero temperature field theories, and eventually we'll see that how these parameters can be used. They appear in certain physical quantities at finite temperature also, and possibly we can bound those, put bounds on those physical quantities at finite temperature. So just getting to the point, the main interest the main thing that I'll talk about is basically the 3-point functions of conserved stress tensors, which for conformal field theories are completely fixed by conformal invariance up to 3 independent parameters. And there has been a systematic, all I'm talking about now is some zero temperature normal conformal field theories. And there has been a systematic study of the possible constraints on these parameters in d greater than 3 dimensions. Well, just to be precise, let us consider the 3-point function for conserved traceless stress tensors in d equals 4. Well, if you take the 3-point function of such a stress tensor, conformal invariance says that it decomposes into these forms. Like there is some coupling dependent constant ns times the conformal structure of that you get by weak contractions of a free boson, similarly for free fermion and similarly for gauge fields in d equals 4. Okay. And as I said, like this ns, nf and nv, these I don't mean to say that in any interacting conformal field theory in d equals 4, this indicate the number of bosons in the theory, number of fermions or number of vector bosons. Yes, at the free limit they do correspond to the number of free bosons, but at any interacting point it's just some coupling dependent constant.
When you say conformal invariance, you included there the conservation.
Yes, yes. Conservation as well as tracelessness. Yes. So and for higher dimensions, this NV is some k forms which appear only in even dimensions. So now the thing is that fine, there are these set of parameters that
in 3 dimensions also there are 3 possible
yes.
Higher dimensions, does the number of structures grow?
No.
It's always 3?
Yes, it's always 3 independent structures.
And arbitrary.
Yes. Okay. Yeah. And so the point is that how we want.
Say we were in 6 dimensions, for instance.
Yes.
Would there be a way? The free fermions and free bosons, I suppose, are always
Yeah.
The third structure, what would?
Some cell, some 3 form. I say. Yeah. So we want to put constraints on these parameters that we saw. Like there are 3 parameters, so we want to put constraints on them. So how do we go there? So there was a nice thought experiment designed by Maldacena and Hofman, where you study perturbations of the CFT at the origin. So you introduce some perturbations at the origin of the CFT. These propagate out in time, and then you measure something which they define as this energy functional over the states created by such perturbations. So essentially you can see that we are actually studying this quantity. Some energy functional defined like this, which is a stress tensor, just to be precise, and you sandwich it between states created by either stress tensors or currents. So essentially you are studying constraints on some 3-point functions. Like if the operator which is used to create the perturbation couples to the currents, it puts some constraints on the JJT correlator, and if it's a stress tensor, it puts constraints on the TTT correlator. So
So what kind of three-point function is it? The time order for three-point function? No.
in a sense, yes. In a sense, yes. Yeah, because like the idea is that you create the state, insert this energy functional, and then sandwich it between the final state. So in a sense, it is time ordered. Like in the sense, like when you actually evaluate it, you need a time, you need some prescription, I epsilon prescription to account for that. So yeah. So I'm just coming to that. So I just described the thought experiment, which is the conformal collider, and like now the idea is that.
Let me ask again. This sounds a little bit like evaluating an operator, namely En,
Yeah.
in the density matrix of the state OO.
Well, there are no.
This is a fancy way of
Yeah. Yes.
expectation
Yes.
and usually, normally when you do that, you need a Schwinder-Kelvin type path interval.
Yes.
Are you going to use that kind of?
No.
Why not?
I think that can be done. Like I mean, that can be done. But like for our purposes, we just need some I epsilon. We just need some normal. That can be done. That is needed if you're doing it perturbatively, I suppose. Like in a path integral formalism, as you said, like with a density matrix. Yeah.
No, it's a question of which one. Even a zero term. If you're evaluating you've got a density matrix,
Mm-hmm.
so you want to evaluate an operator, then you go this way, evaluate the operator, and come back.
Mm-hmm.
Right? Because this part of the density matrix was this way.
Mm-hmm.
This picture doesn't really matter. I wonder if this has something to do with radial vortex. Please tell me exactly where will you evaluate this EN?
So basically what you do is like you have some, like say suppose that my polarization vectors are xy, so xy direction. So what we do is like evaluate
Because the difference state of O on O. Think of O and O.
I mean, if the O projection is that would be just
yeah.
because we normalize it
Yeah.
just into
Yeah.
So
if it was to say that we produce by O,
Yeah.
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 and then you can ask how do you calculate that using
Mm.
operator? And the usual way is to go
Yeah.
and
You can do a particular for the numerator and a particular for the denominator.
Yeah.
Good way, I would say.
Yeah. So the thing is that the way this is done is not from the path integral.
Not from path. You
not
use
from.
some
Yes.
okay, fine.
Yes.
Fine. So if
Yeah.
you don't not using path vector.
Yes.
Okay.
Yeah. So, by the way, I won't be talking about evaluating this. I can just tell you afterwards. Yeah. So then the so-called conformal collider bounds is that the expectation value of such an operator over the states that I just mentioned must be positive. So, and if you impose that constraint, you end up having a series of constraints on this NS, NF, and NV parameters. As you can see, I've just written it in terms of T2 and T4, some dimensionless variable, but you can see that essentially they are constraints on NS, NF, and NV.
But just let me ask you about that. NS, F, and NV
Yeah.
are constraints on the time order 3 point.
Yes.
So you have to somehow translate that
Yes.
into the thing you want to do.
Yes, 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 yes.
Maybe because it's 3 points that will. Actually, you're the expert here. Okay, I'll ask you.
Yeah, yeah,
Later.
yeah.
So the issue is whether it's Minkowski or
First, it's related to whether it's Minkowski or
Mhm, yeah.
Now, a single Euclidean correlator continues with many different Minkowski correlators, depending on
Mhm.
So it depends on how you go through the
Yeah.
maths. So I was just wondering precisely how you will get.
Mhm. Okay, so you're worried that the prescription that one might use to evaluate this might not give me.
So given who's done the prescription, I'm sure it's correct.
Yeah.
it's 3-point function.
So there's no issue.
And might be this, even if the four extreme defects.
There are different correlators.
Yeah.
Now it's easy to go from one to the other.
Yeah.
You have to make sure you do it well. Okay. Forget
Oh,
it.
yeah. So the constraints, as you can see now, the point of expressing my 3-point function in that manner, like for some 3-point function of free boson, free fermion, and free vector, is that like you have this collider constraints just reduced to the fact that ns must be greater than 0, nf must be greater than 0, and nv must be greater than 0. So then like again, like in the free fill limit, yeah. So in the free fill limit, then you can see that you can just add arbitrary number of ns, nf, and nv arbitrary number of free fermions, bosons, and gauge fields, and your theory will be causal, because like this, roughly speaking, the positivity of energy flux translates to the fact that your theory must be causal. So this has been generalized to higher dimensions also, and as I said, like there are only 3 independent structures. Like T2, T4 are again just dependent on some ns, nf, and nv, which are for the higher dimensions. And then our question is like, can we use these to put bounds on physical quantities of CFTs at finite temperature? This was all at 0 temperature CFTs, some like Euclidean thing.
This is all CFT in R3, right? Not in
No, R3, yeah.
So simply the property of the OP.
Yeah.
Yeah, I was wondering about the Casimir. Like if you have two-dimensional CFT, then in a finite box in the solution exists the fact of the whole
Mm. Mm-hmm.
So this positivity thing, it must be in some limiting.
It's positive is integrated energy flux
Mm.
out.
Mm-hmm.
It's not a statement that any local energy.
Yeah.
But in CFT, for example, even negative thing, I mean, it's a constant. It's a negative constant throughout the box.
So there's no flux to anything.
So, yeah, so what, there's a flux change there. So
This is, I think, of a flux.
Yeah.
this is a flux.
Yeah, like so you have a circle over which like you're sitting and measuring.
But your quantity is still a function of theta and phi, isn't it? Because you have not integrated over theta and phi.
No, but I have so the point is that in this energy functional, I'm picking out a particular direction over which, yes, you are quite right. It's a function of theta and phi. It will depend on where I am sitting and.
So even that quantity is positive?
Yeah.
I think
I
that-
see, right.
Yeah, like I mean, so essentially the this statement, basically this statement is the fact that this dy minus t minus say y is greater than equal to 0. This is the average null energy condition. That's in some yeah. So then like the statement is that it should be positive for any state that you are evaluating it over.
So at least this level of atom, and like if you're saying that it could,
Yeah.
but then later on.
Hartman and Hartman and you, I think. Yeah, you. Yeah. Yeah. Yes.
Here the justification comes from the probability.
Yeah. So this is now as an assumption, and it was later proved by him and Hartman and all that for any unitary interacting CFT quantum field theory, I think, like this statement is true. So then like that justifies the claim of Maldacena.
It sounds like in an ordinary field theory, only particles need that. So where an S matrix is well defined, the flow of energy on Kreisler is always possible.
Hmm.
So now an S matrix is not well defined. The
Yes.
is zero mass to zero charge. It is continuously. So the infinity so thing is free particles. It's always particle. I think it's very, not very easy.
No, I see. Yeah. I mean, it's just like saying that strand minus minus is only sending
In
and strand
I
minus is
just
only
made it.
giving.
I think it's just that. So it's very intuitive.
Why don't you integrate it one?
Why?
Yeah.
You've got, I mean,
The statement is that like t minus minus by itself might not be positive, like so the you integrate it over y minus dy minus, then that integrated flux is positive.
So picture the curve of it.
Yeah.
This particle being written that way also.
the net wave packet of the particle should carry positive. Then you can make some blip that helps. I don't know. Yeah, I don't know.
So then like so let me just illustrate the finite temperature quantity that we want to evaluate. So they are called sum rules. And what are sum rules? So sum rules are weighted integral over spectral density over the frequencies, and they are proportional to one-point functions in the theory. So schematically, it's like they are given by such formulas, like you integrate over some moments of the imaginary part of the retarded Green's function at finite temperature, and they are proportional to one-point functions in the theory.
So just to say, I think that the idea is to try to make an observable that would measure, if you had a detector in system, what is the net energy flux that you get? How much energy is going through this? I think that's the end. Okay. And that sounds reasonable to me.
So why do we need to study such sum rules? Well, in finite temperature field theory, retarded correlators are very difficult to compute from lattice calculations in say QCD, for example. So there has been a systematic study of such sum rules, but the one-point functions in such theories are like relatively easier to compute. So therefore, like there was a systematic study of such sum rules in context of QCD, and it turns out like you can implement that for CFTs also, like at finite temperatures. So they are sort of like important constraints on the retarded correlators of any like quantum field theory. Like you don't need to compute the actual retarded correlator. Instead, you can put some constraints on them, because the one-point functions are definitely easier to compute. So what are we looking at? So we are actually looking at the retarded correlator for the stress tensor in the shear channel at finite temperature and zero chemical potential. So everything that we do will be with this assumption, with this correlator, and an assumption that I would like to state from the start is that except the stress energy tensor, no other operators get expectation value at finite temperature. Now this might seem to be a bit random assumption, but hopefully by the end of this talk, I can make it clear that even if other operators also get expectation value, the way we derive our sum rules, those operators can be taken care of as well in a systematic manner. So the Fourier transform is defined in this manner, and let us set up our sum rule. So we assume two things, and I'll justify the assumptions just after deriving the sum rule. So my assumptions are that the retarded correlator is analytic in the upper half plane, upper half omega plane, including the real axis, and it dies up sufficiently fast. So then by Cauchy's theorem, I can write down this set of relations where the, I mean, as you can understand, like there was a contour in the upper half plane, and because of this property, it dies off, you just get this contribution from minus infinity to infinity. So now,
your correlator is function omega and k as well?
but I am setting it to 0. Yeah, but it can be done. Yeah. So, so then like yeah, sorry, yeah, definitely. Yes. So then like you can combine these two equations to get this quantity.
And the retarded correlator in the what, thermal state?
Thermal state, yes, yes, in the thermal state. So therefore, like my sum rule is then given by this. Now I will show that this quantity.
Now omega in the period in a finite temperature.
Yeah.
In the imaginary axis is periodic.
Yeah.
So what does it mean that it's analytic in the upper half plane? Wait, upper half plane is real omega Euclidean or Lorentzian?
So so that periodic omega that you say, that comes from like the imaginary time formalism of the theory. But I am talking about, say, the real time.
Good. So when omega is real, are we in Lorentzian space or real?
Lorentzian.
So when omega is imaginary, we are in Euclidean space?
Yes. Yes.
Therefore, imaginary omega should be periodic with the periodicity of 1 by 10.
Yes. Yes.
So what does it mean that it's periodic in the upper half plane? If it's periodic, just
Yeah.
repeats. So then it's periodic as
No. Analytic. It's analytic. Like in the sense like gr omega, the retarded correlator does not have any poles in the upper half plane.
Yeah, but what I'm asking is it true that gr of I omega is same as gr of I omega plus I beta?
No. Yeah. Like. Sorry. Again, can you? Gr of I omega is
gr of I omega plus I beta.
No.
Why not? Two-point functions in finite temperature periodic.
I mean.
Oh, sorry.
No.
I'm sorry. I said that was true in time.
Yes.
So what it obeys is so is it true? So then even worse. I thought that it would be only defined at discrete points. Sorry. Oh, I take it. Sorry.
Yeah.
What's the resolution? I mean, I'm confused as well. I mean, suppose you have in Lorentzian time you have some function like cos.
Yeah. Yes. Yeah.
And then it will become cosine.
Yes.
So clearly the Fourier transform that.
Yeah. Yeah.
But
Yeah.
the analytic we continue. You talk about the analytic continuation of that.
Yeah.
That's defined on the whole complex.
Oh, I see. So,
imagine the Euclidean coordinator. It's defined only at discrete points.
Yeah.
Now you do an analytic continuation.
Yeah.
That is defined on the whole complex.
Yeah.
And you claim that analytic continuation on the upper complex plane is that. I don't know. I presume that the quasi-normal modes that lie on the lower.
Yeah.
Lower.
I mean, it's easy to see from field theory, but from gravity also, like it can be analyzed that the quasi-normal modes actually lie in the lower half plane.
This is presumably a statement of causality.
Yes. Yeah, I was just coming to that in the next slide. Like, so, as you said, like the assumption of that the retarded correlator is analytic in the upper half plane is a statement of causality, and that you can see from the inverse Fourier transform. Like like in order to evaluate this integral, one can close the contour in the upper half plane because for t less than 0 this is a damping factor like e to the power minus omega t, and then like unless gr omega is holomorphic in the upper half plane, you won't have this that the retarded correlator for t less than 0 is 0, which is a necessary statement, which is essentially a statement of causality. So now again I made another assumption that it needs to be it dies off sufficiently fast at high omegas. So then like how do I justify that? So now we look at
I find this how fast you can do that. 1 by omega to the power what?
Okay, like
M for M.
yeah. So now in order to examine the second assumption, we actually look at what was? Okay, rho is imaginary part of G. See, you just take these two complex conjugate and then add that will, yeah. So then like we can just analytically, so in order to understand this divergent behavior, we transform the retarded correlator to a Euclidean time ordered correlator using this prescription, which is valid for the frequencies other than omega is equal to 0, that is n is equal to 0. And now the idea is that since we are looking at very small time intervals or very high omega is where omega is much greater than the temperature scale which is set by the system, we approximate this Euclidean correlator by its Euclidean thermal correlator by its flat space OPE. And this allows us to examine the asymptotic behavior of GR I omega as omega goes to infinity, because you recall like my statement was like in the upper half plane as omega, the upper half plane the GR omega dies off sufficiently fast. So yeah. So
are you going to put constant on GR or in G?
Well, the way I'm going about is like I'll use GE to put the constraint, but eventually it will be like on GR omega. Yeah, like so there are several assumptions that I have made here. One of them is that like one of them is obviously this, which is valid only for high frequencies, and this is justified because I am looking at high frequency. In order to look at the high frequency behavior, I am just using this. So this is justified. Then another thing that we have done.
That is not exact.
That is not true for n is equal to 0.
It's not true for n equals 0, but for any positive n.
Yes. So that's what I am saying. Like that for except n is equal to 0, this is true, and we are safe because we are just looking at n very large. Yeah. And now oh, okay. So what you can one can show is that if you compute the so like suppose like you have this some retarded correlator like OX O0 say, and then its Euclidean counterpart in where so here the thing is tau t, and here it's tau which is IT. So you can show that and you consider the Euclidean time ordered correlator, which is just this. By considering some like inserting a complete number of states, you can show that at this relation breaks down at omega is equal to 0. In fact, there is a delta function contribution at omega is equal to 0.
Is it right that for n negative,
Oh, yeah.
the Euclidean correlator will coincide with the advanced?
Yes.
You see, the Euclidean correlator doesn't distinguish fast and weaker. Retarded correlator does.
Yeah.
So if for some range of n it coincides with the retarded time,
And
for
then
some
on
range of n it coincides with the advanced time. 0 is in between.
Yeah.
It will coincide with that.
Yeah. That's true.
Yeah.
So
Sorry, given the equilibrium correlator, I should be able to reconstruct any equilibrium, any of this type correlator, right?
Yeah, so
either advanced or retarded, like.
No, I mean you can construct time order and anti-time order, and from there you can construct advanced or retarded.
Yeah,
construct
yeah,
everything,
yeah.
but if you just want pure restriction,
Pure restriction.
in the upper half plane will agree with retarded, lower
Yeah.
half plane will agree with advanced, and on the rear axis it will depend on how you
Yeah.
if that makes
Yeah. So your question was like on like
Yeah, I was asking the constant that you are going to put will be on VR or the.
well, I won't be putting any constraints on GR or yeah, it will be eventually on GR. Yes, let's say.
In the upper half plane it will coincide, right?
Yeah. Yes.
No issue.
Yeah.
In the upper, in the upper.
Yeah.
I'm pretty
Yeah,
sure
yeah,
it's
yeah,
like-
yeah, 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 yeah. So, yeah. So let me proceed. So how do you see the divergences, right? As I said, like you can approximate.
It's what divergence is.
Yeah, yeah. So one of the
Actually, didn't get your
okay. So one of the assumptions was that it dies off sufficiently fast,
Yeah.
right? But like we will see
I don't
that.
understand the statement replace Euclidean correlator by OP.
Yeah. So we are taking like very high omegas and therefore very small time scales, and therefore we are replacing the correlator by its OP.
And so the OP is the thing that contributes will be identity. What is it?
No, it contributes a divergent part.
Which operator contributes?
Like the bare so when you take the OP, say the TTOP, you have one which is like the propagators. So the first term that yeah. Yes.
I
Yeah.
know, but the leading one, leading contributor
Yeah.
But another assumption is that the next is the step.
Yes.
Next to the second.
Yeah. That will contribute a finite part.
Okay.
Yeah. So, like I'll just explain it in the next slide. So, like suppose like I take the OPE like this, and I've made the assumption that it's only the stress tensor gets the expectation value, and no other stress tensor or no other operators with delta less than d gets expectation value. So, like if you look at the scales in the problem, like you'll see that by dimensional analysis, this scales, this A hat, this tensor structure scales as 1 by s to the power d, where s is the distance. So therefore, the Fourier transform of these two scale like this. So as you can see very well, like the first term contributes to a divergent part in the retarded Green's function, and the second part is a finite part. So both of these violate our assumption that we have to have a well-behaved retarded correlator to account for. So therefore our retarded GR omega is like this. There is a divergent part and there is a finite part also. So how do we account for that?
But going back, how was that assumption justified that it will die off?
Yeah, yes, I'm trying to justify that. Yeah. So you are exactly right that it is not justified, and therefore we define a regularized Green's function, which is basically, so one of the things is that this quantity, the Fourier transform of this quantity is exactly the same as the Fourier transform of the retarded Green's function at 0 temperature, because these things don't get expectation value in vacuum. So therefore we can regularize our Green's function in this manner, like finite temperature subtract the 0 temperature piece, and also to remove the finite parts we again subtract that finite part that we had, and therefore our Green's function, regularized Green's function, is now both analytic in the upper half plane as well as well behaved as omega goes to I infinity. So now we can restate our sum rule.
So when you say that you are assuming that some heavier operators get
some heavier operator, if it gets 1-point function, it will contribute at subleading orders in omega.
But in the beginning you stated only that.
Yeah. So therefore, like therefore suppose some light operator gets expectation values. So they will contribute to a divergent piece, and you can just systematically subtract it off. Yeah. Yeah. I mean, all the terms which are analytic in omega, like, yeah. Yeah. Like which just go off to 0. So I mean, I'm just removing the absolute divergent and the finite piece. The rest of the terms are all there. 1 by omega, 1 by omega square.
No, but the question was, given that you assume that no other operator will operate.
Yeah. No other operator with dimensions less than d. Yeah.
No, but okay, let's say we take n equals 4 angle still.
Yeah.
In at large lambda, the only operator that gets 1-point function is spectral.
Yeah.
In that theory, will you get 0 when you do the subtraction?
Yeah. No, but there are this descendants of t which.
Okay, descendants of t.
Yeah.
Okay,
Yeah.
No, but the descendants of t are derivatives, and derivatives of translation in there. They don't do.
No, like in thermal vacuum. Yeah. Oh, okay.
The stress tensor function in both ways.
Yeah.
And but the stress tensor expectation value is constant even in thermal space. The black ring is translation in there, for example. No, I think one of the things, if you could go back, you treated this omega to the power d, log omega to the power d,
Yeah.
the Fourier transform of 1 over x to the power 2u
Yeah.
in R.
In art. Yeah.
Whereas the actual thing will be on SD R3 times S1.
S1. Yeah.
So the subtraction is with that thing in R.
Yeah. Yeah.
So the difference between those two will come.
But in the high omega limit, does it really?
No, but he's not asking about high omega. He's asking once you come to subtraction.
Yeah. Oh, okay.
He's asking what's left.
Yeah.
Which is a valid question, right?
Yeah.
Because you really remove the contribution of identity of the stress tensor, you remove everything that contributes, which is just at 0. But I think you're not really removing it.
Yeah.
What you're doing is
Yeah.
removing it in
Yes.
class.
Yes.
Because you don't want to do a temperature dependent
Yes.
renormalization,
Yes.
subtraction.
Yeah. That's
You want
true.
the subtraction to be temperature independent. So the temperature dependence is the physics.
Yeah.
That's what you want to do.
Yeah.
That kind of stuff, exactly. So the first thing is not the full contribution.
Yeah. Yeah.
Still the remaining one would go as omega to the b.
No,
No,
it's the difference between you'll have an exponential damping. You know, the temperature will. The circle has cycle. Like the difference between these two will go to 0 exponentially at larger.
So like so therefore we can define our regularized sum rule in this manner. Like we have the delta omega, and yeah, I just introduced it in the previous slide. So we have a regularized spectral function as well as a regularized Green's function, which is and so and we'll be evaluating this at 0 frequency. Like we will be essentially evaluating this. So here in this regularized Green's function, this
The first term I understand, the subtraction is temperature independent. The second term is it temperature independent?
the second term meaning the
Finiteness.
no.
It's not.
Yes.
You're doing a temperature dependent subtraction.
Yeah. Yeah.
That
I think that may be quite massive.
Yeah. 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 Sorry, again. The temperature dependence is here because this is the Fourier transform of this quantity. So as you can see, the expectation value of the stress tensor is the temperature dependent one. Yeah.
Because that would be 0, 0.
Yeah.
That's the standard OP, thermal OP, right?
No, this is the.
Is smaller than the
Yes. 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 Yes.
So this
That's
is fine.
right.
But now he's defining a new quantity with that being subtracted.
Yes. Yes.
So that new quantity has temperature in its definition.
Yes. Yes.
It's not a universal.
No,
thing
no,
that
no.
we-
That has to get, in this way of thinking about it, that has to come about from the one-point function from the higher operator. Because this is an exact thing that you can do with S is less than.
Yeah.
than
Yes.
So the more temperature dependence of this two-point function would come from the one-point functions of behavior operator.
No, but also
Yeah.
the temperature dependence of T alpha beta of 0,
Yeah.
expectation value has some temperature dependence.
So.
Right. But if you subtract it out as he's doing, then the dependence would come only from the
Higher order of it. But they are safe, right? We can use them to define our.
Let's work on a particular theory. We know that there exists such a theory.
Huh.
Singularity.
Yeah.
Which there's no higher order term.
Yeah.
That has
Yeah.
expectation value.
Yeah.
So I don't think you're going to say that in that theory you're going to get something trivial.
Something. No, I won't begin. Yeah.
So there is something here even
Yeah.
without looking at
Yeah.
higher order.
Yes.
I think that's coming entirely from the first.
Yes. So this will turn out to be frequency independent, right? And we are looking at the subtracted Green's function at omega is equal to 0. So like whether or not like omega is there or not, it will contribute. This will be there. So we will. I'll like as it progresses, you'll see like it becomes the same.
That thing is just temperature T plus 4, right?
Yes. Yes. Yes.
So you subtract out, you get to temperature T plus 4.
Yeah. Yeah. So my regularized Green's function is just so
And that finite, can you just write out what that finite is?
yeah, the finite thing is it will be a one-point function of some proportionality constant, say like c times t to the power 4.
Perfect.
Yeah, no frequency dependence here. Okay. So basically what I am saying is that even if there are other operators which get expectation value, what I have done here is I have just subtracted the most divergent piece and the finite piece. The rest of them are there in my regularized Green's function.
Why is there no log in that theory?
No, like that can be exactly computed. Like, I mean, it is, there is no, yeah. There is no.
Dimensionally, there could have been.
Yeah, but there is
Just
no.
turns out that-
Yes.
That had to be put on.
Yeah.
Okay.
So like even if other operators get expectation, only my requirement is that delta, any operator which gets expectation value, that delta must be greater than d. Then we are safe. For if something contributes for delta less than d, obviously you'll have divergent pieces and you need to subtract them. And there will be temperature dependent subtractions also. So therefore we have our regularized sum rule, and let's just compute the thing. So therefore now we need to get our divergent piece as well as the finite piece to get our regularized sum rule. So we go ahead and Fourier transform the OPE, I mean with proper factors and stuff. Now this is the divergent piece that we know, like it will be, it's just this, it has no temperature dependence and it's just a function of omega. This quantity on the other hand is a function, it's not a function, it's a frequency independent quantity, and it's a function which is just a function of temperature. So this quantity, this A hat, this tensor structure contains information about the 3-point function of the stress tensors that we discussed before. that the parameters ns, nf, and nb. I've written it in terms of ABC, but like you can like there you can just transform
For
them.
all of these structures, the Fourier transforms have no logs.
For the sorry, for which which is the third one?
There are three possible structures for the three-point function.
Yeah, yeah, yeah,
For all of the three of them,
yeah,
you do the Fourier transform and there are no logs.
yeah, 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 yeah,
Is
yeah,
that physical? Dimensional analysis would have allowed it.
yeah,
Because you're doing
Mhm.
dx by x to the power.
yeah.
So dimensionally, naively you would expect a log. So is there something about no anomalous dimensions of that? I mean, is there coincidence as to why?
Why there is no log?
I should be obvious, right? I mean,
Yeah, yeah. Yeah, I have not thought about this, but like, I mean, no.
Yeah, that kind of a log would translate to anonymousness, isn't it? I mean, if
Yeah.
if we put it in the
Yeah.
equation,
Yeah.
then,
Yeah, stress tensors are protected operators, so like the I suppose that must be the reason, like no anomalous dimensions. Yeah. So we can Fourier transform the OPE and we get the finite piece. Oh, of course, we don't care about the divergent piece. Like it will anyways go away as else. And the interesting part is this finite piece. So as you can see, it's just a function of A, B, and C, and just the one-point function of the stress tensor, the pressure.
Wait, I'm sorry.
Yeah.
There's something fishy about this. If there's an operator, if the three-point function which in momentum space is completely analytic,
Yeah.
then in position space the three-point function is purely compact.
In Euclidean? In
It's a property of Fourier transform, right? So how can it be?
no, I have taken the high frequency limit.
So
Yeah.
can be as clear as possible about what you're saying.
Yeah,
So
yeah.
go back to the
Yeah. So what I'll do?
so this is the part with the three-point function. So you just show me the equation. The part which has omega to the 0.
Oh, here.
The forward.
Oh.
Omega to the 0.
Yeah.
Okay.
So a high frequency limit. Of course, like if you just take the Fourier transform of the A hat, it is a function of omega. It is a function of omega and p. I mean, the way we did it was like we took it at a finite omega as well as a finite p, Fourier transformed it, and then took the high omega limit. Of course, in the high omega limit, it's this omega to the power 0 t. Huh? Sorry? Which one? Yeah. Yeah.
Let's say if it was some polynomial.
Yeah.
Then
Yeah.
well, there's a theorem that the only analytic functions that are analytic everywhere in the complex. So all functions are analytic everywhere in the complex. So I just want to understand the statement again. So some form.
Many countries would be right in all the half
Please go on, I'll ask you the
Oh. So, like the high frequency.
I can just ask.
Yeah.
If I take the three-point function, I'm not even sure it's the same question. But if I take the three-point function of three t's,
Yes.
and I try to compute it in momentum,
Yes.
it will be a very complicated.
Yes. Yes.
There's some limit of that function that you're looking at.
Yes.
What is that limit?
The
So suppose I take t of
yeah.
omega 1, omega,
Yeah.
omega 1, omega 2, omega
Yeah.
3.
Yeah.
Some of the omegas are
Yeah.
0,
Yeah.
and similarly p1, p2, p3.
Yeah.
Firstly, you're saying all p.
Yeah. Well,
so let me ask. Suppose I take t of omega 1, omega 2, omega 3. What limit are you taking of that to get what we're talking about?
Yeah. Like so. as such, we are not actually Fourier transforming the 3-point function.
Okay.
Yeah, what we are looking at is the OPE of the 2-point function, which happens to have the tensor structure that appears in the way you get the OPE of the two stress tensors in the subleading order, like you have the tensor structure which appears in the 3-point function.
It's basically the same thing, isn't it?
Yes, yes. So, so definitely, therefore, we are looking at the 3-point function of the stress tensor in the limit that one of these are close to each other.
Okay, and then you take the Fourier transform of that,
Yeah,
and you work in the limit omega goes to infinity.
yeah, yeah.
Okay, thank you.
So what is the important between both initial and final T's are incremental?
Initial and final.
This T, this T and that T, is it not integrated over dy? That so those are.
No, no, I'm not. You're talking about conformal collider physics.
Oh, sorry.
No, no, this is separate. Like this is just some like getting an OPE from the 3-point function. OPE of the 2-point of the two stress tensor from the 3-point function of the stress tensors. That's what I'm just saying. Like the way you get it is consider the 3-point function, take the OPE, take it close to one another. You remove that part where you have the 2-point function of the stress tensor, and the remaining tensor quantity is this A hat.
So is the thing you're quoting is A hat,
Yeah.
Fourier transform as omega goes to infinity.
Yes. Yes.
Okay.
Yes. 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 Yes.
Yeah. What was bothering me is that the statement was that A hat Fourier transform was what he was claiming. Then A hat would have to be delta. Right, because the Fourier transform over there of a constant is a delta. So, but he said it's only true when the omega goes to
Yes. Yes.
Why constant?
Like,
Because he said it's omega to the part zero.
Yeah. I mean, that's what I'm saying. Like it's independent of frequency. Like this term.
But he's only claiming this for omega goes to
Yeah.
infinity.
Yeah. Yeah.
So he's saying that there is a delta function, a contact piece,
Yeah.
and it's removing that contact piece.
Yes.
This is what
Yeah.
you're saying.
Yeah. Yeah.
All you're doing is removing the contact
Yeah.
piece.
Yeah. Yeah.
Okay, sounds perfectly fine. So
Yeah.
now you're going to work with a Green function, which is the same at separated points,
Yeah.
but you just remove the contact.
Yeah. Yeah. Yeah.
Okay, so that's totally easy.
Yeah.
It's the temperature dependent contact level.
Sorry, I thought this A hat goes as 1 over h to the 4, right?
Yeah.
The B.
Yeah.
Why is the contact there?
There are two things you could do. One
No,
over
no.
x to the B or delta.
Delta function is also like one.
But
It's,
you're removing both of them.
No,
No,
he's
no,
only
no,
removing-
no,
the part he's removing in Fourier space is constant, and therefore
Yeah.
he's only removing the contact.
Yeah.
You see, the 1 over x to the part has to be the part that has a log.
Hmm.
He's not touching that.
Mhm.
That was what was confusing.
So there are log pieces.
There have to be,
Yeah.
because how can you get a power without a log? But he's not touching.
Sorry. One thing, like this, I'll be Fourier transforming this entire A hat actually.
The Fourier transform the
Yes,
entire,
yes.
then you take the omega goes to
Yes.
infinity,
Yes. Yes.
and
Yes.
then you're removing the part that goes like omega to the power.
Yeah, but the thing is that after you take the omega to the power infinity limit, only term left is the finite piece. There are no log terms actually.
There are no log terms. What if you had a term that went like 1 over omega to the 4
Yeah,
log omega by 1? Such a term you would not see because
yeah,
you're taking omega to infinity.
Yeah.
Infinity,
yeah,
and it's gone away.
yes.
But I'm claiming such a term has to be. Because otherwise you couldn't get 1 over x to the 4. Let's ask, what is the Fourier transform
Hmm.
of 1 over...
No, actually, like,
If you allow me to work in position, not... It's confusing me also that we're going to omega. Let me work in omega and p, and later take p to c.
yeah,
So suppose I have a Fourier transform of 1 over mod x to the power 4.
yes,
Let me do e to the power I p dot x
yes,
1
d,
over mod x to the power 4.
yeah,
We
d,
can ask what can they answer.
yeah, Mhm.
Now,
You're also looking e to the minus I omega, omega t.
Yeah.
all
The full thing.
full form of that.
Okay, right.
Yeah.
Okay, so now what could this be? So we've got d4p
Yeah.
e to the pi p dot x by x to the power 4.
Yeah.
Okay, so now by dimensional analysis, this is some power.
Yeah.
Okay, but if you just got a pure power, you Fourier transform that back, all you get is a delta function. So the only way that can fail is power times log. You see what I mean?
Yeah. I mean, I understand.
It's a constant or a log in this case, right?
What?
It's either a constant or a log.
Oh,
So log would dominate at omega the
just I'm getting my power there. You're probably.
But
No,
the
le-
Fourier transform that you want is omega 1 over omega square plus p square, isn't it?
Yeah, like that.
So that there is no logarithmic. Again, it's a pole. I mean, so 1 over omega square plus p square.
No, let's do it in the full form of method and then later take p to 0.
Mhm. Yeah.
Yeah, sure.
Maybe we should do it after.
Yeah. 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 Yeah.
Maybe we should.
Yeah. Yeah.
It would be nice on that.
So, like, so maybe we can discuss this afterward. So so the thing is that after we Fourier transform, we get and take the omega going to infinity limit, we are just left with this finite piece, and interestingly enough, so there are two contributions. So since we are working with the OPE, there were some like dimensional regularizations that were that comes into the play while defining the OPE. So forget about that. But the point is, why I have written it in as a sum of two quantities is that this part is exactly one of the channels that Hofmann and after that Myers and all they have found. It's like one of the combinations of T2 and T4 that you get in the conformal collider physics, like that A must be greater than equal to 0. So it's much clear, like if I I'll rewrite the sum rule in terms of the collider variables, then it will be much clear. J was the finite piece, which is the Fourier transform of this. Temperature dependent, since there is a P pressure, the 1-point function of the stress tensor. And so now, what? B? Okay. So in the OPE, actually, when you actually do the OPE from the 3-point function, so you need to regularize it properly because of short distance behaviors. Like you need to take your word identities into account, and for that you need to regularize your tensor structures that are there that were there in the 3-point function. So what happens is that in the OPE you have some regular terms, and then there are some delta function contact terms because of this dimensional regularization. So I'm differentiating the Fourier transform of the delta function just like that. There's nothing. Yeah, you can just consider that. Yeah, that's it. And the reason we did that because like this A was like exactly the combination that appears in the one of the channels in the conformal collider. I showed you like 3 constraints, right? So one of them is actually A, like up to some proportionality constant. It's just that. There are some functions of like that NS, NF, and NB. They are the parameters of the 3-point function. Yeah, that's it. Pressure. Yeah. The 1-point function of the stress tensor, like T say XX is yeah.
Sorry, the Fourier transform of the OP. Which OP was this, please?
Sorry. This one. A hat. Yeah.
Okay, excellent. Yeah. Fourier transform the OP and the obtained
Yeah.
both are constant.
Yeah, both are constants in the high frequency limit.
Yes. You say one comes from the contact term and the second piece comes from where?
Second piece, no. So just maybe it's best to just forget this, like this thing. It's just that in the OPE, if you look, there are like explicitly written out. For example, there are some normal tensor structures, and then there are some delta function like structures which appear because of some dimensional regularization that this Osborne and Petku had done, like in this thing. I'm just differentiating that only. There is nothing. It's nothing significant. Yeah.
Yeah.
What the discussion was about.
Oh. No.
Contact term versus the outcome.
Huh. Okay. Yeah. Yeah. Of course.
The
Like,
A terms come from the tensor structure.
yeah. Tensor structures. Okay. Okay. I misunderstood your question. Sorry.
I'm still confused with it. Yeah, sorry.
Yeah.
Because there is no law.
Yeah, because it doesn't fit.
So then, like, so then we can restate our sum rule. We can evaluate our sum rule, and as I said, like I'll evaluate this gr omega t at omega is equal to 0 from hydrodynamics, and it's just pressure. And you put everything together, and you arrive at this some nice result in terms of the collider variables T2 and T4 that I showed you earlier. Like, so our so this is like completely a finite temperature field theory quantity, but it's controlled by the T2 and T4, the collider variables. So can I? Yeah.
Wait, so now I understood the subtraction. Now delta gr of 0. How did you get that result?
Yeah, so delta gr of 0 is gr0t minus gr0t equals 0 minus a plus b, which are frequency
I
independent.
understand the definition. How did you calculate this?
You input the a and b, and this gr0 is p from hydrodynamics.
gr0 because you've chosen
Yeah.
a particular
Yeah. And then like this quantity, we know that it's independent of temperature. So it's just dependent on frequency.
Okay.
And we can subtract that at 0 omega.
So, and what I'm missing is how you got equation 74.
Oh, you can, the T2 and T4 has some parameterizations in terms of A, B and C. So I've just input them and I have reorganized them.
I still haven't understood. Is there something that have you got this from your OPE or some other?
Yeah, like the OP. So only the finite terms in the OP contribute.
I haven't understood. Could you just go back to your OPE if you don't?
Yeah.
So you took this
Yeah.
and then you evaluated this?
Yeah, Fourier transformed it, and yeah, so maybe
Does dot contribute or
no.
no?
No.
This is the assumption that only P has one person.
Yeah.
Okay. Now next, you did some subtraction.
Yeah.
So what's explicitly what's left after the subtraction? I didn't understand how you got something.
Okay, maybe this is better. Like I can explain it here, maybe.
However,
Yeah. So what I did was like I subtracted the divergent piece and the finite piece.
okay.
Now this regularized Green's function satisfies the two assumptions that I said, right? Analyticity and well-fall of Bayer. Those dot they are there. Okay. I'm not bothered about that. Okay. My use for the OPE was to just get the high, yeah, that's it.
Okay. Then, but now you got some statement about the finite part, right?
Yes.
How did you get? Where did that?
Yeah. So now you try to evaluate it at omega is equal to 0.
How do you do it?
Like putting omega to 0
In what? In which formula?
in this formula. No. I'm just saying that I am using it to just subtract the. So they are like, okay, you are saying that.
Just to start with, what do you know about the GR of omega? At the moment, it's some abstract quantity, right?
Yeah.
So then how do you get something concrete from an abstract quantity? You
mean,
told that, as far as I understood the
yeah.
logic so far, GR of omega, you know nothing about it.
Mhm.
However, you know its short distance behavior from the OP, you use that for subtraction.
Yeah.
But now, in order to get the thing finite, you need the full quantity. How did you know what the full quantity?
At low frequencies we do, right?
From how?
Hydrodynamics?
Okay, so you're using hydrodynamics.
Yeah, yeah,
Okay,
yeah,
fine, fine.
yeah. Like I mean.
Alright, so is there a viscosity somewhere here or not?
Yeah, yeah, yeah. You can have viscosity like over here, but it contributes at higher order in omegas. Yeah.
Ah.
Yeah.
Now I understand.
Yeah. Yeah. Yeah.
Thank you. Thank you. Thank you.
Yeah.
You were doing something at large omega.
Yeah. 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 Yeah.
And then you're setting omega to 0.
Yeah. Yeah. Like I'm just getting my large omega behavior so that it satisfies the condition, the analyticity and the well-behaved behavior condition at omega is equal to infinity. I'm just subtracting that piece out.
So there's no conflict with like setting omega small.
No. It is there even for small omega, right? I mean, that omega to the power d divergent term. It's just that at omega, as omega goes to infinity large, it just diverges completely. At omega is 0, it's fine. Like, I mean, you will still get this Fourier transform is not about like whether omega is small or omega is large. It's valid for every omega, right?
So the contribution of these higher order terms is
uh,
encoded in P.
Yeah.
Everything interesting here
Yeah.
comes from the subtraction.
Yeah.
The delta GR would have been a very
Yes.
simple quantity without subtraction.
Yes.
It's just a little P.
Yeah.
And then the subtraction was P times something interesting.
Yeah.
And so that's
Exactly.
the difference.
Exactly.
But then how is it justified that nothing else gets allowed?
Yeah. So if you like,
The stuff that is
yes. So if you have web, like some operator which is say another some operator which is exactly same as stress tensor and get some expectation value like delta is equal to d, you will just subtract it from the finite piece. It contributes to the
the behavior operators do have to get some
some value. Yeah.
If this constraint is
Yeah. But like, so what I'm saying is that my dealing with the OPE was just to get the high frequency behavior. That's it. Like I'm not taking in principle, so that's a separate thing altogether. Like I'm not setting omega is equal to 0 in the OPE.
Also, I don't think I agree with that. You know, because there is a theory in which none of the operators get, heavier operators get there. When they exist.
But then
It's different between the finite term and the subtraction.
Yeah.
The subtraction is only at omega.
Yeah.
And then he evaluated omega was to 0.
Yeah.
The other way.
but so is it the convergence of the OP that is
Maybe.
thermal
Maybe.
because that's valid only for
Yeah.
Yeah.
Maybe.
So, this delta G, you know, this is very also.
Any CFT.
So, if you are given a CFT where a higher bit operator is there,
Yeah.
when is it evaluated?
No, that's what I'm saying. Like my only dealing with the OPE was to get the subtraction. That's it. I'm only worried about the high frequency behavior.
It would formally run up, it wouldn't do the OPE value. When you want to evaluate that omega
Yeah.
was 0, you don't
Do the OPE, exactly.
Oh,
Yeah. So we have our sum rule, which is in terms of the collider variables T2 and T4, and therefore we would like to check it for theories which are okay. So we would like to evaluate it for theories which are possible to which are dual to two derivative gravities. Dual to two derivative gravities, Einstein gravity. So,
in the previous slide,
yeah.
I don't know what happens to the field when I see equation 24.
Yeah. Okay.
Like you're saying that you have something that you
Yeah. So the this T2 and T4.
I don't know what polite conformal.
Yeah. So just for just for argument's sake, just think of them as some combination of parameters of 3-point functions. The significant thing is that these appear in these are for zero temperature field theories, but we find them appearing in the finite temperature calculations also. That's the only thing. And since there are bounds on these quantities, we can just use those bounds to on this finite temperature quantities also. Yeah, like I mean they are just some bounds on some parameters, right? I mean they don't care about the temperature or no.
I mean, I don't know how they prove it, right? Do they contain some sharpness?
Yeah, like I mean yeah, I mean they
The
continue.
bounds on 3-point function.
Yeah, that
The bounds on 3-point function.
yeah.
Apply the 3-point function till learn
Yeah.
something about.
Yeah,
But then that gives you a bound on the finite.
yeah. On this,
OP coefficient.
the
One can get a
yeah. I'm
Yes, and now he uses that to deduce something
Yeah.
about the finite.
yeah this GR0, the spectral density. So I have essentially it's some like nomenclature, right? I mean like imaginary part of like the retarded correlator.
Because it's inserted a complete set of
Yeah,
weights.
it
Because
becomes
the weight of
yeah.
zero,
Uh-huh.
state, lemma, Callan lemma.
Yeah, Lemon can. Yeah. So like the for CFTs which are dual to the two derivative Einstein gravity, these parameters are already known. Like this A, B, and C. So we can use them to evaluate our finite pieces that I said, and for example the relevant tensor structures that were there, they contribute to this quantity, while the contact term is just some pressure. Yeah.
Going back to the previous thing,
Yeah.
example. So you had multiple quantities. You had the capital A, capital B, and the CR.
Yeah.
How many calculations are constrained there?
All I need is conformal invariance. I'm just explaining it in terms of parameters of 3-point functions, which is universal to any CFTs.
See, it's not calculating, it's parameter.
Yeah.
Because GR is the pressure of the theory.
Yeah.
That's for sort of identity.
Yeah.
Now he doesn't know what the pressure is.
Yeah.
So
I'm
the
not.
element is its-
Yeah.
Okay. Similarly, those subtractions in terms of
Yeah.
ABC. He doesn't know what they are.
Yeah. Yeah. But the point is that this is valid for any CFT. If you know the ABCs of the CFT, you can calculate that. And that's what I'm going to do in some examples.
And also, what about the other side? What about the angular spectral rate, rho omega? How do you calculate that?
Rho omega, sorry.
Yeah, you take a rho omega.
Yeah, that is equal to this, right?
Ah, so, but yeah, presumably you won't calculate both sides and then make
No, that's the thing. That's why some rules were formulated. Like because you don't know rho omega. If you know a particular theory where you can calculate the rho omega, possibly you can check the sum rules. And I think that has that has been done by Son to some extent. I think for n equals 4 super Young Mills, at least he rules out some form of the spectral density using the sum rules, which is consistent with.
So, what are you trying to do with numbers? Like, how are you putting it into
So the motivation behind is that I don't know how to compute the retarded correlator fully. So therefore, at least the least I can do is put some bounds on it. And the way you do that is by considering sum rules.
you want to bound is T.
No, GR0. So let me.
He wants the ratio of GR0 and T.
Yeah.
That's what he will do.
So basically GR up to some factors is just proportional, let me just say. Roughly. Okay. So I'll constrain this. It's just I'm by delta GR0, I just mean that I'm evaluating this. I'll constrain this. So since the point is you don't even know what rho omega is, but I'm able to tell you some bounds on that.
I see. So, you're trying to infer properties of rho omega.
Yeah.
When you wrote down this equation, it was assumed that it uses the behavior.
Yeah. and then try to using
Try
the
to just get such a function by moving the direction.
yeah.
These inequalities might imply something for the higher derivative gravity or something.
I'll come to that also. Like I'll compute these sum rules, the shear sum rule in high derivative gravity setup, like directly from gravity.
Some constraints on the potential.
Yeah. And let me just proceed. So for dual to Einstein gravity, the CFT is dual to Einstein gravity. It's just this. If you just put it everything by hand, like properly with, you just get that delta GR0 is just this. It's just 1 point function of the pressure, the pressure times some proportionality constant. Okay, and for d equals 4, this becomes this, and this we have reproduced the Son and Romachke result for such theories. N equals 4 superangles basically.
Presumably they did the same way.
Yeah. So
I mean, I think
the same way, we have generalized their method to higher. So now we have something which is we can get from conformal invariance and hydrodynamic behavior, but now we are looking at the setup of CFTs which are dual to Einstein gravity, and therefore one of the ways was to actually input the parameters of the 3-point function, as I did just before this. The other point would be more concrete evidence of this, whether the sum rule is correct. It would be to actually evaluate retarded correlators directly from gravity. That people know how to do. How to compute retarded correlators directly from gravity, apply the subtraction scheme, and therefore get the sum rule. This is, I emphasize, is completely different from the that OPE method that I just shown. And it will be clear that for Einstein as well as for CFTs dual to high derivative corrections with high derivative corrections, this is true. Like this, the sum rule is correct. The one we get from just assuming conformal invariance. So these are some references of like the previous works in the literature. I won't go over them. So I'll just outline the procedure of calculating this sum rule from gravity for say n equals 4 superangles, and then I'll just state the results that we have got for higher derivative theories. So how does one calculate it? One studies the equation of fluctuation of this operator in the dual Einstein gravity theory, and the logic is that this operator couples to the stress tensor in the boundary, and therefore you can there is a prescription using ADS-CFT prescription, you can get the retarded correlator at the boundary. That means at the strong coupling. Now, for n equals 4 superangles, such a fluctuation obeys this equation of a minimally coupled scalar in ADS background, and in order to examine the high frequency behavior, after all, as we saw, like what we need is essentially the high frequency behavior. The high frequency behavior has a divergent piece as well as a finite piece. So we will study the high frequency behavior of the retarded correlator directly from gravity. So in order to do that, we make some parameterizations, and like one thing to note is possibly like that as lambda tends to infinity, this which is equivalent to saying omega goes to infinity, this quantity, this equation is just the equation of minimally coupled scalar in pure ADS5.
But you have one correction, right? Because you want to see
Yes.
the graph has been
Yes. So we'll systematically expand the phi's in orders of 1 by lambda and impose and find a solution perturbatively to lambda to the power
You
4.
just need the first.
Yes, yes. We find that like the second correction does not contribute to the finite piece, let's say, or divergent piece also for that matter.
That's clear from the fact that you only had one T to do.
Yeah, yes, yes. So, so the
Sorry, maybe this is give,
Yeah.
here you're definitely doing lambda equal to infinity.
yeah.
And the previous calculation that you showed, there is a 6p over 5, that stuff. I mean, okay, so you're doing hydrodynamic.
Yes.
So therefore, what are the equals force dynamic theory is going in there? I mean,
The parameters A, B, and C.
the parameters A, B, and C.
And these are operators.
Yes,
Yeah,
yes,
yeah,
yes,
yeah.
yes. For n equals 4, super n. Yeah. Oh, lambda here is not actually the lambda.
It's lambda.
Sorry.
Yeah. Yeah, they are not renewable. I mean, they are not renewable.
Because you were looking at conserve.
Yes, yeah.
Because, because n equals 4, the stress tensor is the same multiplicitors. With long term.
Yeah.
These are not.
So,
The chiral primary, chiral
yeah,
primary.
yeah. So we should be able to reproduce the 6p by 5 thing. So after solving everything, like what needs to be done is to input the phi's in this on-shell action, which has also some contact term, which just gives you some pressure function. And the interesting part comes from here. Okay, so therefore, like we again, similar to the field theory calculation, we'll find if you input the solutions of phi. I have not written down the solutions of phi, but like I can tell you some modified Bessel functions and stuff. So you find that there is indeed a similar divergence, which is like omega to the power 4, which scales as omega to the power 4 log omega, and you have to subtract it. And incidentally, the finite piece just comes to be this. So like you don't need any parameters of the 3-point function. It's just some analysis of the this gr omega at high frequency that we do from ADS-CFT. It just lands up in this thing.
Wait, but this was, I thought you wanted to evaluate omega equals 0.
Yeah. So I'm just saying that I'm evaluating the in the subtraction part from gravity. My sum rule is same. The sum rule is same. All I need to do is to look at the finite as well as the divergent part. And in gravity, I do that by directly looking at the retarded period.
So the P cancels the P?
Yes,
And what's left
yes,
behind is the sigma.
yes,
Right?
yes,
This
yeah.
is the trap, I see.
Yeah. So this has been, so this was also done by Son, and
Does that suggest that in gravity, the A is just not a function? Is it true that A is just not a function of omega?
yeah, it's not a function of omega.
No, I mean the full 3-point function, that if you evaluate GR as a function, as I
No. So one of the things is that like we find that
Let me ask again. It sounds like what you, no, I thought. Okay.
so what we find is that I'll just go back some slides, like just keep this proportionality constant in mind. Okay, that yeah.
Gravity calculation, just calculate A and B.
Yeah.
Nothing, just
No.
A and B.
Yes.
Yeah, the only thing that was striking about that is that the GR of 0 cancelled only B entire.
Yeah.
And the full result came from B.
Yeah.
I was wondering whether it was an exception.
In field theory also, if you at the weak coupling limit, if you input the parameters of the n equals 4 superyoung will say that P that B is P. So just keep that proportionality constant in mind, that d into d minus 1 by 2 plus d plus 1. So now let us look at our sum rule from field theory. So you see that in our field theory sum rule, it seems like for CFT is dual to Einstein gravity, only this part is there, and these two quantities are not there. It's an independent check of the fact that for CFTs which are dual to Einstein gravity, that T2 and T4 are 0. T2 and T4 can be separately computed from gravity in completely independent calculation, and it can be shown to be 0. Conformal collider physics. Yeah, 3-point function. Yeah. Huh? Sorry. Which? Sorry. Yeah. Well, T2 and T4 are independent of each other. So, like if their sum has to be 0, it means they individually have to be 0. So, I mean, T2 and T4 are functions of A, B, and C, and they are independent of each other. Two independent parameters.
You could have T2, I mean, what I'm saying, they got numbers.
Yeah.
That term could something. He's saying it's not as strong as the fact that T2 and T4.
Well, I skipped one part. Like so, for n equals 4 in d equals 4, you have also this constraint that A is equal to C, the central charges. So they together with this condition imply that T2 and T4.
I mean, we know that T2 and T4.
Yeah.
Consistent with that.
Yeah. So the point is that in our sum rule, the coefficient, the T2 and T4 were 0, right? I mean, so we have no way to check whether like for some CFTs with non-zero T2 and T4, whether our sum rule actually coincides with our field theoretic derivation. Our sum rule that using that OPE method was just some thing based on purely conformal invariance and low energy hydrodynamic behavior. Now, like whether that is still consistent for theories with non-zero T2 and T4. And yeah. So what we do is like we do it for Gauss-Bonnet as well as some general curvature corrections in higher dimensions, arbitrary dimensions. So, well, I would say like we have not checked the coefficient of T4 in our calculation, because in order to compute non-zero T4 you need cubic interactions. We have not done that. We have only gone to quadratic corrections to the Einstein-Hilbert action. R cube, Riemann cube curvature. Yeah. So we do it for Gauss-Bonnet theories, and it's the same procedure. We just evaluate some differential equation. We need to solve this differential equation in the high omega limit, and we find, I'm just skipping the details of the calculation, it's the same essentially. We find that our 6.5 by P is corrected by this lambda Gauss-Bonnet dependent term. Now, the T2 and T4 for such theories were also already computed. And we find that inputting this T2 and T4 into our field theoretic sum rule, we get our gravity, we obtain a match with our gravity calculation. We now extend our thing to arbitrary. So Gauss-Bonnet was some specific combination of these couplings. So we now extend it to like arbitrary dimensions and some like arbitrary parameters like C1, C2, and C3.
Most general 4 derivative.
Yeah, most general 4 derivative, and to linear order. C1, C2, and C3.
But the linear order C1, C2, and C3 is always the field rate definition.
No, but not for C3.
No, you can't get rid of C3, but
Yeah.
you need to make it Gauss-Bonnet.
Yeah. To linear order, yes.
So then there's nothing new, right? You're working to linear order.
Yeah. Sorry, I'm.
If you work to linear order in C1, C2,
Yeah.
and C3,
Yeah.
you can always make a field redefinition to change this into Gauss-Bonnet.
Yeah.
Then it has to. If
Yeah.
Gauss-Bonnet works,
Yeah, 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 that's true. Yes. Yeah, I mean r square and r, these
can
two
get rid of
terms,
that
yes,
actually,
absolutely.
or
Yeah,
set them to any value.
yeah, yeah. So like our sum rule then becomes this, and to check we actually compute T2 and T4 holographically, like from the 3-point functions to leading order in C1, C2 and C3, and we find that it matches our gravity sum rule. Well, so now, so therefore we have checked our sum rule up to this coefficient up to T2 in our sum rule, and now we would like to use the collider bounds on the T2 and T4 to put bounds on our spectral function. So
Can you go back to the previous slide?
yeah.
So what Shiraz is saying is that C1, C2 and C3 are not gauge independent?
No, no. C1, C2 can be got rid of by some up to linear order.
So therefore, only their overall scale is, I mean, I can always make, 1 minus 4, 1.
Yeah, 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 yeah.
And only
Yeah.
the overall scale is
Yeah,
one,
yeah,
so
yeah.
only one of the constants.
Yeah,
should appear
yeah,
in your
yes,
calculation.
yes,
And that's visual.
yes, yes, yes. That's the thing.
Yeah, C3 is the only one you can't shift by the way.
Yeah, yes. Two linear order. So that is also consistent with this field redefinition thing. So now like we are again back to our field theory results. Now we know the bounds on T2 and T4 for any CFT. The holographic CFT with holographic dual was some subset of this special case. So we find that this causality bounds restrict our sum rule, that is this integral over the spectral density, to lie between these, and we find that the lower bound is saturated for theories with only free fermions, and upper bound is only for theories with free gauge fields.
Since the ends couldn't be negative,
Yeah,
it's reasonable that some ends being 0 are
yeah,
saturated.
yeah, yeah.
Number of
Yeah, 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 yeah. Yeah, yeah, exactly. Yeah, that's how we found.
The bosons which are discriminant.
Yeah, it lies somewhere in between. Like so this can be done for the general sum rule, and we have this quantity. Although for d equals 3, it's a little bit special because you have just only one independent collider parameter for theories with no, which don't break parity, for example. Like
There is no real theory there is a real theory whose stress tensor is just pure free permeable.
yeah.
That's the theory of free permeability. But there's no real theory whose stress tensor is just pure free bosons, is there? Oh, you're saying
No,
U1,
U1, yeah. Yeah. So for d, yeah. So for d equals 3, our sum rule bounds are somewhat different, and but still it falls within the general bound. You can see it like, yeah. So what we have done essentially is we have put bounds on our spectral density, which is a finite temperature field theory quantity, using completely some arguments from zero temperature field theory. Well, one can actually try to see that for these ABCs for n equals 4 super Yang-Mills at the free limit is just gives you that, well, epsilon is 3p, so you have like 6p by 5 for, and that's as he was saying, like for n equals 4 these ABCs are not renormalized, and yeah, so.
And this ratio, the 6 by 5 for n equals 4, is just the weighted sum of the number of bosons, number of fermions.
Yeah, yeah.
Which one gives 2? Was it the gauge bosons?
Gauge bosons.
fermions with
Fermion,
halves and
yeah,
scalar sum in the
yeah,
middle,
yeah,
all weight stuff.
yeah, yeah. And
D equals 3 is saturated by bosons and fermions.
there is no gauge bosons, so sorry, gauge I mean gauge field, so it's just bosons and fermions. The upper half is the bosons, scalars, and the lower half is the fermions. As
And the all structure plays.
it is there, but yeah.
But it doesn't saturate the bottom.
Well, interestingly, for the shear channel, the parity odds structures don't play a role. For in the sense that if you were to evaluate delta GR0, the parity odd parameter does not appear for the shear channel. So we have also evaluated it for a host of theories, like with well-known gravity tools, and in fact we had done the same for this large n Chern-Simons theories, where you just that pi lambda, like n by k, so thing, and I'm just showing you some like you were asking like whether the Fourier transform has some like like log things or not, but like this is the full analytic structure of the
that's great.
For some other channels, for example T, Tx, Xz, for example. So this is like
What's PZ square? Or PZ?
Pz is like this thing.
So it's not a Lorentz. So this is very important. So this is what I was saying wrong. I was thinking of something that was essentially Lorentzian. You're getting something that's not Lorentzian.
Yeah.
That's what I was thinking. That's somehow very.
Actually, we were doing the entire calculation, that OP Fourier transform in Euclidean space actually.
Yeah.
So like.
But
the
fact that there's a circle is mattering or not?
No, because we are looking at the flat space Euclidean.
Then I don't understand how you can get PZ squared by omega squared plus PZ squared. What is PZ?
The momentum along the z direction, and omega is the momentum along the t direction.
Why isn't the rotation invariant? You're saying that the temperature is mattering, right? The fact
That
the
P.
circle is mattering.
That p.
Fine.
I'm saying that it's not mattering.
But it's not Lorentzian.
The polarizations are also breaking.
Yeah.
Because it's Tx, Tx. It's Tx, X.
But if we transform all the momenta, it will follow same vector. I mean, he just
Yeah.
I understand. I see.
Polarized will be this vector.
Yeah, that's right.
Oh, that's true. That's
So the question, as PG points out, is what is distinguishing between omega and p? The left hand side looks symmetric between the two if you forget about the finite.
Yeah.
Right hand side is not symmetric. How symmetric? Presumably the fact that the temperature matters so much.
I understand what you mean. Maybe I need to look at these a bit more carefully. Maybe I have not. You're saying like it's independent of this thing. Maybe I can just Well, I'll just conclude by saying that like this. So what we have done is we have found the spectral density constraint, the sum rule for the retarded shear channel of the retarded correlator for any CFT at finite temperature but zero chemical potential. We see that the causality constrains the shear sum rule to lie within the specific bounds. We have also evaluated the corrections to the shear sum rule for theories with high derivative corrections to Einstein gravity, and we find that indeed they are modified by from the two derivative Einstein gravity dual, And we also see that let me just point out I'll look at get back to you. The point of showing you this was that the other parameters, the Hofman-Maldacena parameters, actually appear in the subleading omega limit. So you can see that, like in the other two channels they appear in the subleading omega. So like one needs to possibly formulate a new sum rule for these channels to say something using the Hofman-Maldacena constraints. And also for d equals 3, I think like the parity violating coefficients will appear in the other channels. The vector, it does not appear for the tensor channel that we have checked, but like it will appear for the other channels, and it would be probably interesting to find some rules for that.
Choose your polarization
Yeah,
in such a way
yeah. That the odd term is clicked. Yeah. That's the point. And certainly one of these polarizations will click, like TXXZ maybe. Yeah. So.
EXXZ will under spatial,
Yeah.
type.
Yeah. 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 So. Yeah. So. Okay.
Bangalore.
Oh. Yeah.
Mumbai.
So the linear, the fact that you are working, I mean, in the R square thing context, up to linear order in C1, C2, C3, that's because of what?
Sorry, I don't understand. Like.
You could take that theory
Yeah.
as it is,
Yeah.
and you could do your calculations.
Non-perturbative.
To let's say quadratic order.
Well, I don't know the solution. Like one has to, I mean, one can in principle do, but like I have just worked to linear order in C1, C2, C3. It can be, of course, be done.
But
Yeah.
Shirazi's argument could still
No,
be
but
valid.
no, that linear, only in linear order can you get rid of C1 and C2.
Isn't it something that you using offshell? I mean, what is to the Lagrangian itself or not?
It is to the Lagrangian, but that's it.
Yeah.
So suppose we take a Petri definition of square root g r,
Yeah.
and we do a linear transform.
Yeah.
Then that is proportional to equation of motion times change. So that's r mu nu tensor.
Yes.
And so now if you choose that something to be g mu nu, you can get rid of the r term.
Yeah.
You choose that something to be r mu nu, you can get rid of the r square term. But all this is all linear. Right?
Yeah. So I have the transformations actually, like if you are interested, like, so if g mu nu goes to
So non-perturbation is still different.
yeah.
So then we said the period jump. I mean, suppose. Yeah. It will be arbitrarily high density.
You can't be limited.
Yeah,
Yeah.
no problem. Right, because
So using this transformation, you can just do linear order, but there will be some C I square terms in the action left over.
Yeah, I should just make a comment that the 3-point function,
Yeah.
even if you have all the operators,
Yeah.
no anomalous dimension,
Yeah.
Calvin symmetric equation does not include logs.
Right.
It's only 2-point functions
Yeah.
where lambda and there's only one momentum,
Yeah.
and lambda and p appear in the same way. So if you have what I mean is cutoff.
Yeah.
Lambda del del lambda plus gamma acting as a 2-point function equal to 0, and if gamma itself is equal to 0, then it can only be a power law in lambda. Therefore, it becomes a power law in p.
Okay.
Because it can only be a function of.
Yeah.
However, there are in 3-point function there are 2 p's,
Yeah.
doesn't, you can make some statement about overall scaling
Yeah.
of P.
Mhm.
So of all the P's together.
Mhm.
But that does not preclude something like log of P1 over lambda minus log of P2 over lambda.
Mhm.
You know, I don't know exactly what structure this would appear, but I'm
Mhm.
saying that you cannot make an obvious statement that you cannot have logs when you have more than 2-point functions.
Yeah, but like my thing was just 2-point functions, right? I mean, it's just that the OPE
So
is.
your final statement was about Txy, T alpha beta, or is it?
Well, yeah, in some limit, like when one of them is close to the other.
I see. If it is only the 2-point function, then I'm confused again.
Yeah,
I mean,
why?
it's,
Like,
how is it consistent with current equation? Normally, you.
I mean, can you just?
Yeah. Well.
Yeah. Mhm.
So I'm saying that you have this kind of a statement. N gamma plus beta equal to this stuff
Mhm.
acting on the 3-point function. So a 2-point function.
2-point function.
Okay, in this case it is just 2.
Uh-huh.
Okay, this guy is equal to 0. Now
Mhm.
this fellow is a function of, depending on the overall anomalous, I mean, if the engineering dimension is something like this, then it is some f of t over lambda.
Yeah.
So this fellow acts on that.
Mhm.
Okay, so this overall thing, you know, just brings in some Oh, you. Oh, that's my dream. I'll do this. So yeah, so this is some lambda to the power 2 delta,
Mhm.
and if you take this, so in fact it comes with this. With this, it becomes gamma. Yes. Now it's only the fp by lambda part. Now I'm in a conformal field theory, so betas are all
Yeah.
0. So I have just this.
Hmm.
This guy acting on
FP by lambda.
fp over lambda is equal to 0. So now what people do is to change that variable to p plus gamma
Mhm.
acting on f
Hmm.
of p over lambda to 0.
So you are transforming this.
That's right. It's a minus
Uh-huh.
minus p thing.
Mhm.
And then if gamma is 0 also,
Mhm. Then you have power law.
Yeah.
Yeah. So the
That's what the usual
Yeah,
argument is. Why
yeah.
in a conformal field theory, two-point
Yeah.
functions were power
Yeah.
laws. If you look at yeah, in a
Mhm.
conformal field theory,
Mhm.
you have power laws for two-point functions.
so like, but like this is independent.
What Shiraz was looking at was some, I mean, this coefficient which was a function of the 1-point function of t.
Yeah. Yeah. Yeah.
That essentially was the 3-point function.
Yes. Yes.
roughly speaking,
Yes.
in the OPE.
Yes. Yes.
So for that, I don't know what to say, because that's not this equation. There you have 3 momenta.
Yeah.
Like P1, P2, P3,
Yeah.
P3
Yeah.
equals
Yeah.
minus P1 minus P2.
Yeah.
So therefore there are 2 independent momenta, P1
Mm.
and P2.
Mm.
So then this is not the scaling.
But like that tensor structure is essentially like.
Yeah.
So, but that tensor structure is essentially some function of 1 by s to the power 1 by s or s, and I'm just Fourier transforming e to the power I omega t. There is no like 2 or 3 moment. There is just only one momenta.